the discussion that we had earlier on Butterworth filters, and we want to do this in the context of how to actually design a Butterworth filter and how to choose values of R, C1, and C2. So once again, figure 15.21, and I'm just going on this section of the video to just go through what's basically in your textbook. So you can follow along, or you can just read the textbook as opposed to watching the video, or you can watch the video, or you can do all of the above. So figure 15.21, as you recall from the previous lecture, shows the circuit that gives the second order transfer function that we want for the Butterworth filter. So we'll just go back to our table. Here's that table of Butterworth polynomials. And so what that's doing, what that circuit is doing, is it's implementing a single one of these second order. So like in the fourth order, you have 2 second orders cascaded. In the sixth order, you would have 3 second orders cascaded. In the fifth order, you would have a regular op-amp filter, and then you'll have 2 second order filters cascaded. So you can see that basically what's changing is this middle number. So here's the circuit that is available to implement that. And then if we analyze that circuit, writing note equations, as we showed in the previous lecture, we get this equation. So what we want to do is we want to make this equation look like whichever one of these Butterworth polynomials we're trying to implement. So the first thing that you want to do is you want to replace this term in the numerator with a 1 for the prototype filter, meaning this term will also go to a 1, and meaning we can just choose a variable for this middle term in the denominator. So first of all, setting r equals 1, we eliminate r from the equation, and then we can let 1 over c1, c2 equal 1, meaning we have a transfer function that looks like this. And in this case, 1 over c1, c2 is 1, and then b1 is 2 over c1. So b1 is going to be the number that you see in this middle term of this Butterworth polynomial, whichever one it is you're choosing to implement. So b1 is going to take on different values, which means that c1 and c2 are also going to take on different values depending on what the specific design is. But you know that this relationship, 1 over c1, c2, is always equal to 1. So the order in which to do things is we're going to use this equation, and we're going to use these two equations. And we've already selected a prototype filter that has a cutoff frequency of 1 and a resistance of 1 ohm. So the next thing to do is to work with this B1 term so that we can define what C1 is. Once we've solved for C1, we can then use this equation to solve for C2, and then that allows us to solve for all of our components. So here's an example of a fourth order Butterworth filter. In this particular example, we want a cutoff frequency of 500 Hertz and a passband gain of 10, using as many 1 kilo ohm resistors as possible. So basically this is a repeat of the fourth order Butterworth filter in example 15.7. So the first thing we do is we look up the Butterworth polynomials for a fourth order filter, and we see that we're going to need to cascade 2 second order filters together. And then we look and we see that the middle term here is 0.765. So if we come back up to this equation, that's basically B1. So 2 over C1 is going to be 0.765, which gives us 2.61. And then we also know that 1 over C1, C2 has got to give us 1. So that allows us to solve for C2. So in that first stage, C1 is 2.61 and C2 is 0.438. Then we come here and we see that C3 is 1.08, because now instead of using 0.765, we have to use 1.848 for our number to determine C3. So in this case, 2 over C3 is 1.848, C3 is 1.08, and then C4 comes from 1 over C3, C4 has to equal 1. So now if we put these capacitors into our circuits and 1 ohm resistors, we basically have a fourth order Butterworth filter that will have a cutoff of 1 radian per second. Now we take 500 hertz and we multiply that by 2 pi, so we find that our desired cutoff frequency is 3141.6. So that sets then the frequency scaling factor that we need to use that will give us a cutoff frequency of 500 hertz. Our magnitude scaling factor, we're told that we want to use as many 1 kilo ohm resistors as possible. So the difference between this problem and some of the previous examples is in this case the resistor value is specified, and that's going to fix the magnitude scaling factor. So our magnitude scaling factor is 100. Taking then the frequency scaling factor and the magnitude scaling factor together enables us to get a factor by which to multiply our capacitors to get our new capacitor values. And so when we do that, and we take our old capacitor values and we multiply by 1 over Kf, we get the following capacitor values with a 1 kilo ohm resistor. So our circuit then looks like this, and then the final stage just gives us, if we use a 1 kilo ohm resistor for the input resistance, we need a 10 kilo ohm resistor in the feedback loop. So this is our Butterworth, our fourth order Butterworth filter with a gain of 10 or 20 dB in the pass band. So that's basically the procedure that you go through in order to use the Butterworth polynomials along with scaling to design a Butterworth filter given certain specifications. The next thing that I want to talk about is a little bit more of a design problem, and that is a lot of times you won't necessarily be told a specific filter order, but you'll more be given a set of specifications on how rapidly you want to attenuate your gain in the transition band. So here's a classic low pass filter where we have a pass band, and then we have a transition band, and then we have a stop band. And we'll just define this gain AP, or this magnitude AP, and omega P, and a magnitude AS and omega S as just some arbitrary points. Because a lot of times you'll be told, well, we want you to design a filter and we want the cutoff to be 500 hertz, and then we want between 700 hertz and 1500 hertz an attenuation of a factor of 10. Or sometimes it'll be given as a number, sometimes it'll be given in dB. So if we say we want to attenuate by 40 dB between 700 hertz and 1500 hertz, the question is, what should the filter order be? So basically, the value AP is 20 times the log of the magnitude of the transfer function, which for a Butterworth filter is given by this expression here. And we can express this as this factor under the radical sign to the minus 1/2 power, meaning we can bring a minus 1/2 out front, giving us minus 10 log of the factor under the radical sign. And at point AP, that occurs at this frequency omega P. At frequency omega S, we would have AS, where AS and AP are in dB. So then, using the definition of the logarithm, we can take 10 to the power minus 0.1 AP and 10 to the power minus 0.1 AS and express them in terms of omega P and omega S. And then do a little bit of algebraic manipulation on the equation, and you can get a ratio, omega S over omega P to the power n, is related to the quantities in these two radicals, which are then given as sigma S over sigma P. And then we can basically take the logarithm of each side, allowing us then to express this in terms of a logarithmic ratio. And now n is going to be our order. And so the reason to take the logarithm here again is that then isolates n and allows us to solve for n, given specifications on omega S, omega P, AS, and AP. So if you're given an AP and you're given an omega P and you're given an AS and you're given an omega S, you can actually solve for the filter order that you would need by using this equation. Now, if we assume that if we simplify this by saying omega P is the cutoff frequency, and then AP would be minus 20 log base 10 times the square root of 2 because cutoff frequency is designed as the square root of 2. That then makes sigma P equal to 1, and so this expression for N simplifies somewhat. If we use a Butterworth filter to achieve a steep transition region, then the filtering specification makes this 10 to the minus 0.1 AS much, much greater than 1. So we can actually further simplify by setting the sigma S approximately equal to this quantity, which then means basically the log base 10 of sigma S is minus 0.05 AS. So after that's all said and done, basically a good approximation, assuming you have a fairly high order filter, a good approximation for the order that you need is minus 0.5 AS divided by the log base 10 of the ratio between omega S and omega P. And note that it doesn't matter if this is in radians per second or hertz, because once you divide it, it's unitless. So once again, if this is your cutoff frequency and you're given some specification for above cutoff, even something as simple as 1 order of magnitude above cutoff, you want to attenuate by 30 dB, then that would tell you basically that you could use this equation to determine what the filter order is that you would need to achieve that specification. So that's just a design parameter that is sometimes used in order to determine a filter order. So here's an example of that. We have a cutoff frequency of 1000 hertz. You would like a gain of no more than minus 50 dB at 6000 hertz. So, and then finally, what is the actual gain in dB at 6000 hertz? So the cutoff frequency is given, so you can let sigma p equal 1. The 10 to the minus 1, this is your a sub s. That's much greater than 1, so you can basically use that equation that was given on the previous page or the previous slide. So if you use that equation, you come up with n is 3.21. You've got to go up to the next whole number, so you would need a fourth order Butterworth filter. So using a fourth order Butterworth filter, you then come back to calculate the gain of the fourth order Butterworth filter at 6000 hertz, and what you find out is that you end up with minus 62.25 dB. So so that is how you would determine the order of the Butterworth filter that would be needed to meet those specifications. This is a topic that is used in filter design and even to a lesser degree in filter design of digital filters to determine the order necessary of a filter to meet certain specifications.